Okay, so there was just one more reaction that we didn't get to cover, one more reaction concerning alkynes, and that is the oxidation of alkynes. For that, you can use either KMnO4 or you can use ozone. The result is exactly the same. The only thing that you need to pay attention to is that the product that you get by oxidation of internal alkynes, when it's internal alkyne, both carbon atoms will become carboxylic acid. But if you have, that is when you have an internal alkyne, but if you have a terminal alkyne, the carbon atom that is um, without hydrogens, that will become a carboxylic acid as well. But the other one, the one that had one hydrogen atom, that will get oxidized at a higher level of oxidation, and that's why it becomes carbon dioxide, CO2. So let's see a couple of examples of that with specific molecules. So there we have in this next slide, we have, this is an internal alkyne, right? Internal, because we have two sp hybridized carbon atoms, and none of them has a hydrogen atom attached to, and the result will be that this carbon atom here will become CO2, COOH, right? And then the other carbon atom there also will become COOH. It's not a bad idea to number your carbon atoms. It's rather easy to get confused here, and then you end up with a different number of carbon atoms. And either the TA who is grading that or OWL, they will be rather merciless. And just because you have one extra carbon atom, they will count it wrong, right? So there you can number here 1, 2, 3, 4, 5, 6. 1, 2, 3. Yes, the carbon number 3 is the one that is becoming carboxylic acid. And then in the other side, this is my carbon 4. This is my carbon 4, 5, and 6, right? And then the other example that I have for you here is an terminal alkyne. There is a hydrogen atom that we are not showing there, right? And the result will be that this carbon atom here will become a carboxylic acid, while the other carbon atom there, that is going to become CO2, right? So it's not so bad, and the good thing is that KMnO4 or ozone, both of them will give you the same result. Okay, so then now let's practice a couple more syntheses. So here we have a synthesis of more complex looking final product, right? So then my advice is that you look at this molecule and you need to figure out what should have been the last reaction that you have performed in order to obtain that product. Well, so here I see a compound that has an OH and a bromine, that they are in opposite sides. Well, actually, the only reaction that I know that will allow me to do that, to make that, will be the reaction of the bromohydrin, right? And what are the reagents necessary for the formation of the bromohydrin? And you need to use Br2. If you are using Br2 only, what will be the result? If you are starting with an alkene, you will get formation of a dibromo compound. But I want to form a bromohydrin. I want to get an OH as well. So I need to use Br2 and water. So what should be the structure of the alkene necessary to synthesize that? Well, so it should be an alkene. And because I see that the two hydrogen atoms here are in opposite sides, so that means the alkene should have those hydrogens in opposite sides as well. That means the ethyl, the two ethyl groups, they are opposite. right? So that should be my desired starting material, right? And then now the question is, in order to get this alkene that is trans, what reduction method should I have used, right? So the starting material should look like this. And in order to get the trans product, I need to use lithium in ammonia, right? Lithium in ammonia. And then in order to get that alkyne, how can I do that starting from acetylene? It will be step number 1, sodium amide. Step number 2, ethyl bromide. Step 3, sodium amide again. Step 4, ethyl bromide again. So in that way we have deprotonation of the alkyne with sodium amide. Then I have alkylation of the acetylide anion that I have produced, acetylation with the bromide, with the ethyl bromide. In that way, I attach one of the ethyl groups, and then I have deprotonation again with sodium amide, and a second alkylation that will attach that, and then I go reduction with lithium in ammonia. That will give me the trans product, and then bromination in the presence of water. That will give me the bromohydrin with the bromine and the OH in opposite sides. Okay, let's go to just one more example. So in this example, the final product, I have a cyclopropane with a couple of chlorines hanging there. So the very last step should have been the use of chloroform and KOH, because in that way I can form the so-called dichlorocarbene that will add to an alkene. What kind of alkene will be this, cis or trans? The fact that I have hydrogen and hydrogen both as dashed lines, that means that the alkene was a cis alkene, right? And I have this other group here and the methyl group there, right? So what kind of reduction should I have performed of the corresponding alkyne in order to obtain that product? Well, the reduction, it should have been a reduction that will give me a cis product. So the appropriate reagent will be hydrogen in the presence of a Lindlar catalyst. And then once I have determined the alkyne that I need, so then I need the sequence of deprotonation, alkylation, deprotonation, alkylation. Here, it doesn't matter the order. You can do the alkylation with the methyl first, and then the alkylation with the, what is this? This is an isobutyl after, right? So you can go NaNH2, followed by CH3I. That will install my methyl group there. And then I can go deprotonation with sodium amide and alkylation with the bromide of that, right? So there you have the complete synthesis. So I will stop here, and then in the next video, we can get started with the next chapter.